we shall continue on talking a little bit about electric potential and then talk about capacitors. Let's look at this picture I have at the beginning just to get us started. This has a positive charge Q located between two parallel plates, so the electric field is constant. What's going to happen to that positive charge Q? Okay, it's going to be attracted by the negative, repelled by the positive. So it's going to go like that, right? And so if I wanted to calculate the work, how would I calculate the work done on that charge? It's what? It's the force dotted with the distance. Since they're parallel, the force is the same direction as the distance. They're going to be just force times distance. The force is going to be QE, whatever that electric field is. And then the distance will be, I'll just put D here for the distance. So the work is the charge times electric field times the distance. So if I take that, I can say, okay, what's the voltage difference that it goes through? How's the voltage difference going to relate to this? The definition of delta V is delta U over Q. Well, how do we get delta U? We get delta U by saying that work net is equal to change in kinetic energy, and change in kinetic energy plus change in potential energy is the change in overall energy, or the work non-conservative. And in this case, we don't have any non-conservative forces. The electric force, just like the gravitational force, is a conservative force. You can do work against it, it just stores the energy and gives it back. And so the work non-conservative is 0. And so now I can put everything together. If the work non-conservative is 0, that means change in potential energy is equal to minus change in kinetic energy. Delta U is exactly the same thing as, it's different textbooks use different symbols in different places for potential energy. U means potential energy, PE means potential energy. I'm sorry about confusion between symbols. I know my picture here has PE for potential energy. What does the textbook have for potential energy? I think it's PE, right? Yeah. Sorry for that confusion. So since the change in voltage is the change in potential energy over Q, change in kinetic energy is equal to work, I can put that all together. So the change in potential energy is minus change in kinetic energy. Change in kinetic energy is the work, and the work is QED. So the voltage difference is just electric field multiplied by the separation. So between two parallel plates that set up a uniform electric field, or any place where you have a parallel uniform electric field, if you're traveling parallel to the electric field, the voltage difference is just the electric field strength multiplied by the distance you travel. And if you travel the same direction, yes, minus sign, is that what you're raising your hand for? Yes. Thank you. If you travel the same direction as the electric field, I realized just as I started to say this, your voltage goes down. If you travel the opposite direction, your voltage goes up. And without that minus sign, it would have said the opposite. So I thank you for noticing that. So just a starting point here. Another point that we like to make. Units. What are the units for work? Joules. So if I take this QED, it has units of joules, right? But I can also take this, and we just worked out that ED, the magnitude of ED, is the change in voltage. So I'm just going to use the magnitude here and say that the work is equal to Q times the change in voltage, right? And whether it's positive or negative depends on if it's positive or negative voltage. And in truth, of course, it should have had the minus sign. And so in terms of units, What are the units of Q? Coulombs. And what are the units of voltage? They're volts, but a volt is a joule per coulomb. So you see it comes out to be joules. But we go one step further. Usually when we do something like this, we're doing it with charges that are like 1 electron, 2 electrons, 1 proton, 2 protons. So they're all in integer multiples of the charge of an electron. And so we introduce a new unit for the energy that is the electron volt. If I had Q equals plus 1e, that is if it's a proton, or if it's a singly ionized atom, then my work would be 1 electron charge multiplied by the change in voltage. And once again, you have the sign out here. And so we say, let's make a really easy unit of what we call an electron volt. So let's just take the unit electron charge and voltage and call that an electron volt. We use that because it makes it real easy. If I have an electron that goes through a voltage difference of 1,000 volts, then the work done is 1,000 electron volts. Right? You don't need a calculator to do that math, right? If it was 695 volts, it would be 695 electron volts for the work that was done. So that's what the electron volt is. And if you want to compare an electron volt to a joule, you just say, well, that's the charge of an electron, 1.602 times 10 to the minus 19 coulombs, right? That's charge of an electron, times a volt, which is a joule per coulomb. So 1 electron volt is the same as 1.602 times 10 to the minus 19 joules. So it's just a very convenient unit for us to use. And you'll see we like to be convenient, so we like to use that unit. Okay, our first, I didn't open it. Give me a second to open it. Our first of only 2 clicker questions, so you have to answer both of them. So you can answer starting now. Sandy and Paris are the only ones who have answered at this point. A point charge always naturally moves to a position of lower potential energy. What does this tell us about the natural motion compared to electric potential? And yes, this was where we ended class on Wednesday. All right. So we ended up with some votes moving around. But a very large majority this time saying that positive charge moves to lower electric potential while negative charge moves to higher electric potential. And that's absolutely correct. It's moving to lower potential energy in both cases, but positive charge has a lower potential energy when it goes to negative. And so that's positive going to lower electric potential because electric potential is lower at negative charge. This here is a statement that just goes with what I started with. The electric field points in the direction of decreasing voltage. All right, a simple question. I think you had one like this on the homework that's due today, didn't you? I think I signed one. A battery-powered lantern is switched on for 5 minutes, so I have delta T equals 5.0 minutes. What units should I use for time? Seconds. So that's going to be 5 times 6 is 30. 300 seconds with 2 significant digits. And we have a total charge Q is equal to minus 8.0 times 10 to the 2 coulombs. And we have the work is equal to 9,600 joules. Through what potential difference do the electrons move? How in the world can I calculate this? Do what?
The equation for the change in voltage.
Okay, I need an equation that's going to relate the change in voltage to the, well, actually that didn't say work, it said change in potential energy, so let me change it. To change in potential energy. So just going back here, we had the change in potential energy is minus the change in kinetic energy, which is then going to be minus QED, or change in voltage is minus ED. Well, we don't have a distance, do we? Nope. So we have to think about this a little more. So if I have a change in energy of 9,600 joules, and I have my definition that delta V is change in potential energy over charge, what is delta V going to be? And 96 divided by 8 is 12, right? So we had a voltage difference of minus 12 volts, the way I calculated here. And so it turned out it wasn't hard. It was just using the definition of what voltage is. But it seemed like I might have to do something a lot harder. Okay, I've already talked about this slide to death. This one here is pretty obvious. Voltage is a scalar value. How do you add scalar values? You just add them. Right? There's nothing tricky about it. And so if you have two charges and you want to find the voltage somewhere due to those two charges, the electric potential due to those two charges, you just take the electric potential due to one plus the electric potential due to the other, add them up. A lot easier than finding the electric field, because the electric field I had to add them as vectors. And in the calculus class, we'll learn that you can just take the derivative of the electric potential to find what the electric field is. That equation is, I think there's a minus sign. So it's not a hard calculation. It does involve a directional derivative to get into a vector. So this is a problem that I'm not going to do because I think I'm going to run low on time. It's just saying, what's the voltage, what's the electric potential at two different locations? Well, you just go through that. KQ over R is the voltage at some distance R away from a charge, and you add them up. So coming back to spherical conductors. With the spherical conductor, we determine some things about charge and electric field. So if I have a spherical conductor, spherically symmetric conductor, where's the charge going to be located? On the outside. If it's positive, that means that on the outside I have what condition? I have missing electrons on the outside. But on the inside, everywhere except for on the surface, I'm going to have an equal number of protons and electrons. Just on the outside when that's going to be broken. If it's a negative charge, what does that mean? Have extra electrons on the outside, still equal numbers of protons and electrons throughout except for on the edge. And then what's the electric field going to be? Let's say it's a positive sphere. So I have a sphere with a positive charge. What's the electric field going to look like outside of that sphere? Okay, it's always going to be pointing normal to the surface, pointing away. And the strength of the electric field is given by KQ over R squared, where R is the distance from where to where? From the center to wherever my point P is. Right, it's not from the surface, it's from the center. So we have the electric field direction going radially outward if it's positive, radially inward if it's negative, and the strength. What about electric potential? The electric potential doesn't have a direction, so we don't have to worry about that. The electric potential we learned for a point charge, it had the equation of V is equal to KQ over R. And we learned that the electric potential the change in electric potential is proportional to the change in the electric field. So there's going to be some relationship between the electric potential and the electric field. Now I said proportional. It's not linearly proportional, clearly, because you have over r squared and over r. But here's graphs of the electric field and I don't have a magenta, so I'm going to go with this, and the electric potential as distance from the same charged sphere. What's the one thing that looks significantly different? The what?
First part.
Okay, the first part. For the electric field inside is 0. But if the electric field inside is 0, what does that tell you about the electric potential as you move around? It has to be constant, because we saw from the work we just did that let's go back to it rather than just say we did. Here, that the voltage change is electric field times distance. And so if there's no electric field, then the voltage change has to be 0, so the voltage has to be constant. And so that's why we can say it's obvious that it has to be constant voltage in there, because there's no electric field. So anywhere inside of that sphere would be a constant voltage. Now, before I even go further, somebody here was talking about Faraday cages recently. And a Faraday cage is basically you put yourself inside of a conductor. So if you're inside of the conductor, your electric field inside the conductor is 0. And so the voltage is constant. The voltage can be 100 million volts. But if it's 100 million volts here and 100 million volts here, the charge has no change in energy going from that place to that place. So if I touch those two places, since there's no energy difference for the charge, it doesn't go flying through me. If there was an energy difference, if I touched 100 million volts here and 0 volts here, well, there's a huge difference in energy per charge, and the charge is going to go flying through a pathway, my body, and that becomes hazardous. So inside the Faraday cage, you see them, they put it so you have arcs of light, or arcs of electricity flying to that Faraday cage, and it looks scary as all sin. But the person's inside just calmly, writing a letter or typing or something, because inside your uniform. So Jordan sent me a video that I wasn't able to watch of an airplane being struck by lightning. Now, when that airplane is being struck by lightning, that's kind of scary, right? And as I was saying to George just before class, from what I've read, approximately 10% of all airline flights get struck by lightning. Obviously, your airplane doesn't necessarily come down when you get struck by lightning, right? Why not? Because your airplane is essentially a Faraday cage. You have an aluminum exoskeleton, that's a conductor. And so inside, everything's pretty much protected. Now, I say pretty much because everything we've done so far is what we call electrostatics, stationary conditions. Electrodynamics, when charge is moving, doesn't fully follow the same rules we've been talking about. And so there can be damage done when you're struck by lightning. But generally there's not. And you're inside, you don't know what's going on, you're buffing around because it's a storm, and that's it. Well, statistically, I've certainly been in an airplane that was struck by lightning, but I've never known of any lightning striking an airplane. Now, a second thing that was different about these two is the shape of this versus the shape of that. You notice that the electric field drops more rapidly and then flattens out. The voltage drops more slowly. Why? Well, because this one here, once again, behaves as if it was a point charge once you're outside of it. And so it's KQ over R, whereas the electric field was KQ over R squared. So that's why they have different shapes out there. Biological systems. How many people here are interested in biological systems? That is pre-med, pre-dent, or such? A majority, right? So I try to put these in because they will hold more interest to you than they do to me, honestly. So how do our bodies use electricity? Well, one way is our nerves operate by electricity. You're sending electrical signals essentially down a wire. Now, it's a complicated system. It's a system that I clearly don't understand, okay? So I'm not going to try to explain how the nerves work because I don't, biology is not my field and I haven't spent time on it. But you have voltage differences that cause an electric impulse to go down a nerve, and that's how all of our communication inside our body is basically done. Well, at least what I understand of communication. I have no idea how your body says, oh, I have damaged tissue. I need this kind of molecule to fix it. It's magic. This I know a lot more about. I mean, who hasn't had an EKG? I've had EKGs. I've had electroencephalograms. The electroencephalogram is actually really cool. They were studying pain response under hypnotism, and they used the electroencephalogram to actually see what our brain was getting from pain, and then they compared that to what we said about the pain. Do you guys know how to ethically induce pain in a test subject? The approved standard is not doing things like sticking needles in you. It's by putting your arm in a bucket of ice water. And, initially that's okay. After a minute, it really starts to hurt. And so, it's been 30 seconds. How bad does it hurt? It's been a minute. How bad does it hurt? That was the research. And then they're checking my brain waves to see what my brain was saying about it. And then they have the people who actually were susceptible to hypnotism, who they did the same thing with when they were hypnotized. This isn't going to hurt at all. Does it hurt? You guys ever been hypnotized? For this, they did a hypnotic screening. And it was really funny because he's like, your arm feels heavy, heavier. You'd really like to lift your arm, but you can't because it's too heavy. Try to lift your arm. I'm like, looking around. Huh. Yeah, the guy afterwards said, yeah, it was very clear. You were unhypnotizable. Some people are maybe. Yeah. And, of course, what makes you hypnotizable or not? It's not strength of mind, as John Candy would tell you in the movie Volunteers. You guys haven't seen? You really should watch it because he plays Tom Tuttle from Tacoma, Washington, who just graduated with an engineering degree from Washington State University. Go Cougs. And he teaches after the communists brainwashed him, he teaches them the WC fights on this. So you have all the communists marching, fight for Washington State, win the victory. Okay, so that's not important here. I know I was talking about something. Oh, yeah, okay. The hypnotism is also not important here, but you have to kind of want it. You have to say, I'm going to let that person, tell me what to do. And so I'm sitting there saying, no, my hand's not heavy. And so I wasn't hypnotizable. Whereas I'm all, well, he said it is, and he wouldn't lie to me. Yeah, it's your mental state. Okay, so another one that I know a lot about, being an EMT, back when I took the EMT class, we had to learn to read the EKGs because we had defibrillator and we look at the EKG and we say, ooh, I can shock that, or ooh, that's a non-shockable rhythm. They actually, at the end of my time as an EMT, they took away our defibrillators and gave us ones that didn't give a readout, and they just tell you shock or no shock, so that way the EMT can't make a mistake. The machine makes the mistake and is responsible if something happens bad. Okay, so this picture here is what we call normal sinus rhythm. Rhythm, a word that I spell wrong every time. Does it have two H's? Yes? Okay. I got lucky this time. Well, what is going on with this EKG? As EMT in the field, we have simple rules for the EKG. I only put 2 on. Sometimes you put 3 on. Sometimes you put, 6 here? And so you have the basic rule, white on the right and smoke over fire, right? Everybody's learned that? Jordan, did you learn that?
I didn't learn that nothing but.
Yeah. White on the right, smoke over fire. So white, gray, red. What are they doing? They're measuring voltage differences across your chest because you have the heart underneath and the heart runs on electricity. Here's what happens in a normal heart. I'm probably going to spend the whole class period talking about a heart and not get to capacitors, but it's important. My EMT teacher was the artist I always wished I could be. He said, "This is the heart." Good with that? Now, of course, connected to the heart, you have the vena cava, superior and inferior vena cava. And of course, the heart has chambers. There you go. The chambers on the top are called the atria. Chambers on the bottom are called the ventricles. There is an old term for atria, in case you ever see it. It's the auricles. So we have those chambers. Now what's going on? Unoxygenated blood comes in the vena cava, the inferior and superior vena cava, and goes into the right atrium. Atrium, we all know atrium, right? We have atrium over here. Atrium is just a storage place. So the blood comes in there and stores, and then you have a valve, and correct me if I'm wrong, because you guys probably know this better. I think this is the tricuspid here, which means it's a valve that has, I can't do it with two hands because it has three cusps, not two. Over here we have the bicuspid, which only has two, also called the mitral valve because the Pope's mitre, you know that hat, has two cusps. So the blood goes through there when you have an electrical signal. So how's the electrical signal work? Once again, my EMT teacher was very simple. You have up here the SA node. The SA node is where the nerves from essentially the body's pacemaker, or the sinus, whatever, come to the atrium. So SA is the sinoatrial node. And so you have electrical signals that come there. Now the heart is a complicated device. Those electrical signals then travel, the color is not a wise choice, it turns out. Choose, there's color. So the electrical signals go all through the heart. So the heart's three-dimensional, right? And they're going through the atria, all through them. And as they go through, it causes the muscle to depolarize. Depolarize, you have a drop in the voltage. And so the muscle depolarizes as it goes through. When the muscle depolarizes, it contracts. And so that signal going through the heart makes the heart contract, and that pushes blood through. If it's the right atrium, it goes into the right ventricle. If it's the left atrium, into the left ventricle through the either tricuspid or bicuspid valve. The electrical signal basically gets connected here at what's called the AV node. It's the connection between the atria and the ventricles. And the AV node, believe it or not, I don't know how God designs these systems, but it sits there and it collects the energy, and then it sends the energy down through the bundle of PHYS. So if you've ever heard of somebody that has a bundle blockage or a bundle branch blockage, it's blocking the electrical signal going through that bundle of PHYS spelled H-I-S. And then you have finally your little Purkinje fibers that go out into the ventricles and send electricity to the ventricles to make them depolarize. Muscle goes and you go on. Your heart beats. Now, what happens if things don't work? Anybody know what happens if your atria fail? You don't. You don't die at all. In fact, you can have your atria both dead and get a pacemaker. You don't want a pacemaker in that case. And your heart is still somewhere between 75 to 85% as efficient as it would be without. Because you do have a gravity feed there, and the blood will go from the atrium into the ventricle on its own, even if the atria don't pump. But the atria help. Then you have the ventricles. If your ventricle doesn't work, then you're dead. So taking things like, I assume no one here has a pacemaker, but it's possible. People get pacemakers because our body has ways of responding to failures. What if your atria die, right? You have no electrical signal anymore because the muscle's dead. Well, the AV node's sitting there saying, hey, where's my signal? And it will fire on its own. So your heart will beat about 40 beats per minute, even if the atria are doing nothing. And of course, if that happens, then we say that you have a bradyrhythm, you're bradycardic, because your heart's going too slow, a sign that you're not getting the signal through the atria. Well, what if you have a bundle blockage? Well, then you're kind of screwed, right? Because you have nothing to tell the ventricles to fire. Well, your body will send a signal about 20 beats per minute for the ventricles to work, even if you have a bundle block. So you'll still have your heartbeat about 20 times per minute. 20 times per minute's probably not enough to stay conscious. So you'll lose consciousness, but you don't just die when all of the electrical signals are blocked. But it's nice to have a pacemaker to make it so they're beating at the right frequencies and whatnot. So pacemakers in an ideal situation, you have a pacemaker here, and if the signal doesn't get there, it just tells the atrium to go, and it goes from there. But atria are there to try to get signals that make sense in terms of the frequencies when you have a significant problem. Okay, now going from that to this picture, this is what normal sinus rhythm is supposed to be. And so do you guys know the pieces of these voltage signals? Yes, good, because I have a clicker question coming up on it. So let's go through the very basics. We start with the letter P for this thing right here. And so what's going on with that P wave? It's what? It's actually the depolarization. Depolarization of atria. What that means is you have the signal going through your atria, the muscles contracting, and you're pushing blood from the atrium into the ventricles. So that's what that first rise is. So if somebody's atria just aren't doing anything, no voltage going through it, that could be a flat line. And like I said, that's not good, but it doesn't kill you. Then we have the next part, which is complicated. And because it's complicated, we use a complicated name. That's the QRS complex. It's called the QRS complex because you have multiple things going on. You have the repolarization of the atria. So part of that is the atrium is now getting ready again. So the muscle is resetting. That's the repolarization of the atrium. Part of that is the depolarization of the ventricle doing its pumping. And so QRS complex is repolarization of atria plus depolarization of ventricles. God didn't create us so we could look at the heartbeat on a scope, right? He created us to work efficiently. And so, the way these come out in time on top of each other is not a problem. Then we have the final one that we see here, and that's the T wave. And the T wave, running out of space on my nice work, Richard. Well, I'll put it up here, even though it's out of place, is the repolarization of the ventricles. So that's what it's supposed to look like. Now, how can things go wrong? Well, a decade ago now, I had some issues. I had some blood clots in my lungs. And over time, it got worse and worse to where I couldn't walk down a hall without taking a stop to catch my breath. Right? It was really bad. And my physician kept saying, there's nothing wrong with you, nothing wrong with you. So finally, went home for Christmas break, had my brother do an EKG, and he looked at the EKG, and I had normal sinus rhythm when I was just sitting down. But then he had me do jumping jacks for a minute and did it again. And after doing jumping jacks, my T wave was inverted. Yeah, and I'm like, My brother's all, that's not good. And so when I came back to Lincoln, I made an appointment to see my physician. He still didn't think there's anything wrong with me. Don't go to Dr. Gregory Hurlbut. Okay, Gregory Hurlbut will try to kill you. Just so you know. Really, really pissed me off because he's still like, there's nothing wrong. Even if you have an inverted T wave, sometimes those just happen for no reason. Sure, sometimes it means your heart's dead. And I was insistent, fortunately. And so he wouldn't even look at the EKGs I brought with me. I didn't get paid for doing those. I'm not going to do those. So he did his own so he could get some more money. And at that point, even resting, the T wave was inverted. He's all, really, it's nothing. But I was insistent, and so he sent me a specialist. And then I actually got called that night. Not to make you panic or anything, but you need to be in the hospital. Now, it doesn't have to be this minute, but within the next hour, you should be there. Dr. Hurlbut never came to visit or anything. I was in the hospital and refused to treat me when I came out. So, don't go to Dr. Hurlbut. Everybody got that point, right? Yeah. Gregory Hurlbut, because there's two Dr. Hurlbuts. I think they're brothers. Greggorylhurl. Okay, anyway. So that inverted T wave, what did it mean? It meant that my heart wasn't getting enough oxygen. And so why did I have to go to the hospital? I had to go to the hospital because the blood pressure in the right ventricle is elevated because of the blockage. And so, they go in and they do their quick measurements, and it was like 90 millimeters of mercury in my right ventricle. It's supposed to be 25. Right, so I had over 3 times the blood pressure on the right side, and that's more than that's made to take, and so worried about that causing a heart attack because the heart's trying to pump too hard. So these things, they save lives, like mine. So, that's why I spend so much time on it. So, what part of the EKG is produced by the recovery, the repolarization of the ventricles? This was not worth having somebody discuss because it's just a row memorization type question. Everyone, but okay. So we had 4 that said a P wave and 17 that said a T wave. Now, I'm just going to call on people to answer what each one of these are, except for I'm going to skip the first and last ones. So what is a P wave, Jerry? Okay, it's the starting wave, is correct. And what's going on in the heart at that point? Electricity going to? Okay, so it's depolarizing of the atria. Contraction of muscle. Okay? Q wave. Okay, it's part of the QRS. The Q wave, if I remember properly, because it's always part of the QRS, I don't pay a lot of attention. I believe that's the repolarization. Yeah. That's the repolarization, I believe, of the atria. The R and T, I have never seen a clear separation of the two, so I'm going to ask, or the R and S, I mean. I've never seen a clear separation. So combining these. What's going on with the RS? Going to the back row, Carrie. And finally, Nate, what's the T wave? I heard somebody helping you out. I'm pretty sure you knew what it was, though. The repolarization of the ventricles. Now, I skipped two. The J and the U. Those are not commonly seen. The J wave, if it occurs, is, oh, wait, now I got to think about that. Yeah, the J wave, if it occurs, is right there. And that's, I think, principally caused by hypothermia. So it's pretty rare. So that's the J right there. And then the U is a very weak signal here. I don't remember exactly what caused the U, but it's so small, it's very rarely observed and nobody cares about it. So I put them on here because they are parts of the heart rate or the electrical signal. Why do I go through all this? Just to help you understand the things we're looking at here are very practical. What they're doing when they put these on is they're just putting little sensors on your chest to measure the voltage difference between 2 points. And if you have a 12 lead, that's what the picture here is for a 12 lead EKG. If you count them up, there's nowhere close to 12 there, right? And I think there might be one or two, yeah, you've got some ground ones I think that are missing. But what they consider a lead in the 12 lead is each pair. They consider each pair a lead. So you take those and you could just take 3. Well, if you take 3, you'd only have 3 of these. But if you take 4, you would have more than 4 pairs that you can make. And so that's why the 12 lead doesn't have 12 wires. So just measuring voltage differences. In lab, we're going to use a multimeter, measure voltage differences. We actually have the equipment. If you want, you could do an EKG using just our lab equipment that we use all the time. All right. Already gone through this, right? I worked this out before we started the lecture proper, that the voltage difference is minus electric field times distance. And so here is now essentially the same thing that we started the class with, but we're going to ask, oh wait, maybe we're not going to ask. I thought this was actually a problem saying, what is the kinetic energy when the electron comes out? Well, the kinetic energy when it comes out is actually a real simple calculation. If the electron, the electron is obviously going to be repelled by negative, attracted by positive, so it's going opposite direction, as the electric field. And if it goes through a voltage difference of 5,000 electron volts, what will its kinetic energy be when it comes out? Or if it goes through a voltage difference of 5,000 volts, what will its kinetic energy be when it comes out? How much work will be done? Yeah, 5,000 electron volts is the work that will be done because it'll be the charge times the voltage difference. And that work is converted into kinetic energy. So how much kinetic energy will it have? 5,000 electron volts. So if you know that it's 5,000 volts from here to here, then you know that the kinetic energy will be increased by 5,000 electron volts. Now, we don't use cathode ray tubes for our televisions anymore, but this is the essence of how a cathode ray tube works. A cathode ray tube, you have a little electron gun, and that electron gun has a little filament here. You put an AC voltage across it. It makes the filament hot. When the filament's hot, it gives off light, right? That's how incandescent light bulbs work. But it's also going to boil off electrons. So you have electrons coming off. The voltage they use here is a little less than 7 volts. So the kinetic energy of the electrons that come off is going to be less than 7 electron volts. And then They take a power supply, they put over here a screen, and that screen is like 99% open. Yes, they make metal screens that are like 99% open space. And they put it so you have, like, let's say 10,000 volts difference. So what's the electron that comes off of here going to do? It's going to go screaming toward the positive charge. And because that's mostly open space, the electron's going to come out here with the kinetic energy equal to 10,000 electron volts, plus or minus about 7 volts. That's 7 volts doesn't really matter if you're at 10,000, right? And so you have the electrons all coming with the same energy, and then you're shooting that at a screen. Well, of course, the cathode ray tube. Okay, do you guys know what I mean when I say cathode ray tube? Okay, you guys, the TVs you were born with, right? The ones your parents had when you were born. Those are cathode ray tubes. So you're shooting electrons at the screen. But if all the electrons just go straight, you don't have much of a picture. You have a dot. And so we want to make the electrons go up and down and side to side. Well, how are you going to deflect an electron? Yeah. And so after the electrons come out of here, then you put 2 sets of plates. One set of plates that are aligned horizontally, and you put a voltage difference across those. And you just change the voltage. As the electron goes through, it's going to be in there for a fixed amount of time based on its speed. And when it's going through, it's going to have an electric field, have a certain acceleration. Depending on how strong it is, you'll have more acceleration. So you just set the voltage to ramp. So you have 500 volts, 495, 490, and so on. And so the electrons go as it changes. So you might have seen commercials for like ITT Tech, where they show a guy with an oscilloscope looking at the voltages from a television. And you have one thing that's going like this. Those are the voltages for that, for setting the height of the electrons. Now you want them to go side to side, so you have a second set of plates. They're set up like this, with once again a voltage difference. And for that, you want to sweep across. And so for that one, the voltage looks like, nice job on that second line. And so that's controlling the sweep. And so the old cathode ray tube is a great physics example because we're just using what we've learned now with electric fields and voltage to make electrons hit the screen. Now there is one final thing. You don't see the electrons. What do you see? Light. And so on the screen, you have a bunch of little picture cells or pixels. And each picture cell has 3 different types of phosphors. And those phosphors will absorb electrons of different energies. And so one of them will absorb, the highest energy electrons and will give off blue light. One will absorb lower energy electrons and give off green light. One will absorb lower still energy and give off red light. And so you actually have 3 of these guns, and each one, they'll sweep across, and only one of those 3 phosphors reacts to it, and it gives off light proportional to how much electrons hit it and the energy. So that's how a cathode ray tube television works. Equipotential lines is where I'm going to have to stop. We talked about electric field lines. Electric field lines are lines of force. They tell you the direction the force is going to be on a charge. Equipotential, what does equi mean? It means equal, the same. So equipotential lines are lines that have the same potential. In this case, we mean the same electric potential / voltage. And so equipotential lines where you'd have no change in energy if a charge moved along them. Now, if a charge moves parallel to the electric field, you have force parallel to the motion, a change in energy. So the equipotential lines have to be perpendicular to electric field lines, so the charge wouldn't have a change in energy if it went along an equipotential line. And so you can see the picture on the left, the parallel plates. Electric field is nice and uniform. The equipotential lines are perpendicular at all places. And They just change with ED. The one on the right is 2 negative charges. It's a little more complicated to look at, but I think clear. I have to say one thing that I keep forgetting. I told Caitlin I was going to post it on Facebook, and I didn't yet. I think it was you, wasn't it? Or I don't know. What? Maybe? Lab. We didn't have lab last Tuesday, which is not a big problem because what we're supposed to do for lab, what were we supposed to do for lab? Just get our groups together. So please work before class on Monday to find 3 other like-minded souls. Now there will be one group with 5 people in it. So there will be, there's 21 people, 21 divided by 4 is 5 with the remainder of 1, right? So there'll be 5 groups, one will have 5 people, all the rest 4. So basically, the first group that says, we have 5 in it, I will accept. The rest I'll say, you need to cut one out. So email me your group, and I will just take groups by the order they come in. Email me what you would like to do, and I will, if I can't over email evaluate, say yay or nay, I will. If we need to talk further, I'll let you know. So we can get that started, because that's all that we had set for last week. We really didn't miss anything. It was time for you guys to not have labs so you could focus your time at some point in the semester. But please do send me your groups, and let's get started with selecting the topics. Have a great weekend. Enjoy the mass hysteria that shall be coming on